you, and I'm working with Joe and Rick Curian and Kevin Schmidt as my PhD studies. And I've been working on the merging problem for Ewald spheres. I've been developing a Monte Carlo method for doing the merges. I've been doing them with trilinear interpolations, so we don't have to worry about non-uniform Fourier transforms or anything like that. But yeah, so let's see if I can, yeah, here we go. So I'm sure many of you are familiar with the expand, maximize, compress algorithm developed by Lowe and company to do this merge. It's a method based on expectation maximization. There's a bunch of other other ways you could go about this, but this is one that's using a probabilistic sort of approach, trying to create a walk to approach some maximum likelihood solution to our problem here. So yeah, so our goal is to see if we can do this in a Monte Carlo sort of way. It might simplify the approach. It might make it better for using for like cases where we have more degrees of freedom than just orientation. For instance, in these single particle diffraction experiments, which is what I've been focusing on, but potentially there could be more applications here. But for instance, for single particle diffraction experiments, you don't know exactly the like incident fluence of the beam when it hits a particle, because the beam has some sort of cross section. So the fluence is going to be like more intense in the center, and with the beam, if the protein is to the side of the beam, if the protein is to the side of the centroid of the cross section of the beam, it's going to be a different fluence level. So that you can also kind of treat as a random variable. So to do the like exhaustive scan over that space is a 4-dimensional integral. And so Monte Carlo method. Whoops. So the doing these sort of exhaustive integrals over higher dimensions can become really computationally expensive. Like as Iris was just saying, like in this combined merge and phasing algorithm, even the merging part can still be like a limiting factor. So here's the cartoon of single particle diffraction, instant X-ray, some sort of protein target or whatever it is, small, tiny number of scattered X-rays to our detectors. So I'm trying to focus on the single particle idea, where the number of photons you're going to get is really tiny. So maybe on the order of a few hundred. So this is what your data is going to look like. It's really hard to try to orient this thing. Like, how can you tell from what orientation this is from, and especially when you don't know what the protein looks like in the first place. If you listen to Rick's talk yesterday, he derived this sort of equation. And so using, assuming the Born approximation and far field scattering, and which can be true if your target's really tiny and your X-rays are kind of the correct regime, you can get this equation for what the intensity scattered into any particular region is going to be. And so this is the equation that's going to tell you kind of the like pointing vector, kind of like the energy flux. But of course, all of this is photons, and it's intrinsically quantum. So when you get these really tiny fluences or illuminations or diffractions, yeah, this is of course going to be quantized into this small number of photons. And so instead of being a continuous classical electrodynamics problem, you're going to be dealing more so with random variables and probability distributions and things like that. So we're going to take it in that sort of direction. Whoops. Yeah, so I've already kind of talked about single particle diffraction, and I'm sure many of you are very familiar with it. But we might be able to look at things as they evolve over time, or perhaps have multiple conformations. Like there's things you can do with single particle diffraction potentially that is not very possible with kind of this traditional X-ray crystallography. But of course, it's very difficult. So hopefully we can get there over the next period of time. So in EMC, this algorithm, it really is just a like a manifestation of this expectation maximization idea. And so the problem there is when you're trying to find the parameters that maximize the likelihood of your data given some like unknown additional parameters. So you could have a mixture of Gaussians or something where you don't know when any given sample comes from Gaussian A or Gaussian B. You can do these sort of integrals to kind of split them and find the distribution or the parameters that maximize the likelihood of what your data sample is. So it's been useful in statistics for a really long time. But in our case, the parameters that we're trying to solve for, the parameters are the model diffraction volume that we're trying to reconstruct. Of course, if we can do the phase, solve the phase problem for this thing, we can get the protein, the actual three-dimensional protein electron density. But in this case, we just have this diffraction data. And so the model that we're imagining here is that the diffraction data is really like the sampling of a random variable. In this case, it's going to be a Poissonian random variable for these photons. This is what's called shot noise. And so what the EMC thing is going to do is it's going to find the model that is most likely for all your random samples to have come from. And with the diffraction data, these are all going to be these slices through the three-dimensional model, this diffraction volume. But your unknowns are, of course, the orientations of your proteins as they're being struck by the X-ray beam. So this is pretty well easily put exactly into the expectation maximization framework, and you get an algorithm that can create a walk for this. Here's a little toy model interlude that I made on my way of learning how to code and getting a handle on this problem. So this is the sort of thing we're imagining. So we have data sets here. These are like our diffraction patterns. They have not enough photons to be particularly useful, and they're also from an orientation. In this case, the orientation is kind of like you tape a picture to a cylinder, and our orientation is just that it has this like periodicity that goes like if something rolls off the top of the screen, it's going to come back on the bottom. And so these all come from something in these random quote unquote orientations. And so I applied the EMC algorithm to this sort of thing, and so we can see if it can handle it. And so very easily identifies these shots as being consistent with one another at particular orientations, and so it will reconstruct the picture of what is in this case a raccoon. And you can see there's like a nose here and there's ears down here, and that's the like orientational, quote unquote, periodicity that's like happening inside of here. In the case of the actual diffraction data case, it means it's going to be your diffraction intensity is going to be reconstructed in a random orientation, which is fine. Things can be rotated. So here's what this looks like in 3 dimensions. You've seen this sort of picture probably many times if you've been following these talks. So each one of these white rectangle curve things is your Ewald sphere of diffraction data. So this is the diffraction data from all of your individual pixels of your detector placed into Q space, into the reciprocal, the Fourier space. And so these should all be consistent with one another if they're oriented correctly. If there was no noise involved, they would all have common curves where they all intersect. But of course, our data is going to be pretty noisy. So all this has to be handled in a probabilistic sort of way. So this is what your update rule actually looks like when you're doing EMC, kind of a simplified representation of it. So this is the method is iterative. It really is kind of like a not quite gradient descent, but a similar sort of walk towards a local maximum or minimum. And so in this case, this is our 3D model is M, and then we're iterating over time. So our initial model is gonna be, you can just guess random orientations or something similar, and you can get a model that's not particularly meaningful. But you take that as your initial guess, and then the algorithm, by doing these sums, these integrals, inserts all of the diffraction patterns into like a three-dimensional grid in an increasingly consistent way. So what we're looking at is J naught here is fluence, and this is the classical electron radius. But and then the subscript K is just your number of shots, your diffraction pattern, and then R is your orientation. So you're summing over all your diffraction patterns, all your orientations. This is some weights to get the grid that you overlay on orientation space is like kind of looks like a soccer ball or something, and the pentagons are larger than the or pentagons are smaller than the hexagons. So you have to deal with that sort of like inhomogeneity sort of thing, but it's not super important. And then the PK here is the probability of the determined from the Kate diffraction pattern of some orientation given our parameters are for this probability distribution, which is going to be just a whole bunch of Poissonian probabilities multiplied together. Because imagining each pixel, we're imagining each of them as an independent random variable with its own parameter. And so this is going to be a probability, and then this is your actual diffraction pattern, your slice at some particular orientation. So you are putting in all these slices in kind of proportional to what their probability at a particular orientation is. If this orientation is really strongly peaked, you'll basically be putting it in at one orientation, hopefully the correct one. And then this one is making this like insertion into a weighted average. So places where they all intersect, like if you have them all intersecting at 0, then this is going to average all the contributions from all the slices. It's just what this one and similar sum is going to do in the denominator. It is more or less a Riemannian integration over orientation. That's kind of important. And then also you can see that it is more or less a weighted average. But all this comes directly out of expectation maximization framework for this particular form. So we can do that. And so this is kind of the theme of how the algorithm works, the embarrassingly parallelized algorithm. So you have a three-dimensional model, and then you have a set of diffraction patterns, all these Ewald spheres. And so I'm representing them by these little C's, these little macaroni noodles. So each one of these K1, K2, these are all our actual diffraction patterns that we've collected. And so this model can be distributed to a whole bunch of cores. Each core can do the exhaustive integration over orientation, or potentially over fluence, or potentially over any other variables that happen to exist in your experiment, and then average all of those together to get a new model. And then by iterating over this, you'll eventually get convergence into a consistent diffraction volume. So this is just kind of a picture of progression of the algorithm, kind of a small resolution one, so you can't see any like super great details of this one. And then, so what I've been doing is taking this existing algorithm and exploring kind of the possibilities of making it into a Monte Carlo algorithm. And so what is Monte Carlo? Monte Carlo is a casino in Monaco. And so the Monte Carlo is just kind of the name that was attached to these methods that use random numbers to do what could be otherwise deterministic calculations. Sometimes they're more efficient, especially when the like number of dimensions is high. Not necessarily more efficient, but just like more feasible. Sometimes it's just like computationally intractable to do the like exhaustive or brute force or whatever computation. But here's an example of like how you could do a Monte Carlo calculation. If you're trying to get the expectation value of a random variable x, you could integrate x over all possible values with its probability density. Like that's one way of doing it. Or you could just sample x a bazillion times and then average those samples of x will also get you the average. So you can apply that principle to, you can actually reformulate any integral more or less as a sampling of random variables. So you can calculate integrals by drawing random numbers or rolling dice. So, and then the particular method that we're going to be using is a metropolis walk. This is a method that allows you to sample basically any probability distribution you want. It's what you use when there's not like an easy or good way to sample otherwise, but it means it gives you the ability to sample basically any probability distribution. And how it works is by drawing random numbers, you generate a walk through the sampling space. And so this is an example of like a totally random walk, like a drunken walk sort of thing. But how the random walk works like is if there were two-dimensional probability distribution overlaid on this, the walk would sample more often where there was a higher probability, and maybe there would be a second peak over here, or it just started here and then walked into the region of high probability. The walk like attracts to the maximum probability state, but it's always drawing random numbers that would potentially kick it out, that cause it to represent the sample at large. And just by drawing a large enough number of steps, by walking around enough, you should walk around and cover the space in a way that's like well representative of samples. So here's the same update rule, but with the Monte Carlo version. It's like at least looks better. You don't have to worry about that weighting factor anymore. There's no grid on orientation space. That's something that's kind of attractive about it, because you don't have to figure out any of the geometry to go with these spaces that are perhaps like non-Cartesian. But now same sort of prefactor, same model, same sum over diffraction patterns, but now the orientational integral is replaced by just a sum of samples, and each little n here is one step in our metropolis walk. So you sum over all the samples that your metropolis walk came up with, and you put them all in their appropriate orientation, or or fluences or states or whatever it is that you're sampling. And then here's the equivalent picture with the metropolis sort of version. So now the C's here, instead of just like looking at every possible orientation, each of the cores is performing this walk. And how they do this is you propose a new state, and then you accept or reject it based off of a random draw. So kind of the vanilla thing is that you like accept it if it's a higher probability than your current state, but depending on this random draw, it might allow you to accept states that have a lesser probability than where you currently are, which allows you to walk out of maximums and minimums and stuff. So this is a little picture of a bunch of proposed states that are being rejected, or proposed states that might get accepted, and so it'll move and then stay at a particular spot for some number of steps, and then it'll move again that's kind of how it progresses. So here is kind of the initial result. These are kind of outdated now. Here's a couple of reconstructions where I scripted up both versions, both the brute force and the Monte Carlo version, and they both look pretty similar. Not kind of too early to say exactly what the differences are, but you can see that you can see the shape coming into focus in both the reconstructions, and then they both this is the difference between consecutive models. The brute force iteration is gonna drop to 0 difference between successive iterations, but the Monte Carlo one will always have some amount of difference between iterations because it's drawing random orientations at all times. And then this thing, they're at least comparable. It's just kind of an initial sort of thing here. So in addition, you could do Fluence as a random variable. And in fact, you have to for experimental data. And so this is the same update rule, but then just also taking Fluence as a random variable gives you an update rule that looks something like this. And then other additional unknowns. Oh yeah, here's the Fluence result. Similar sort of thing. It's starting to look all right. And then additional unknowns, you could also have, you could potentially have particles that are in multiple conformations or some mixture of different particles or something can be handled also as a random variable, which can easily be handled with this Monte Carlo thing or with any other sort of method. But this is me experimenting with also that sort of implementation. And here's the reconstruction where here's a couple of different shapes, a couple of different proteins, and then some, they're converging to something. And that's my talk. So does anybody have any questions?